Well, good morning from California. Um, I want to thank Clinton Andrews for agreeing to speak today. He directs the Center for Urban Policy Research at Rutgers University, where he is a distinguished professor of urban planning. He will be speaking today on informed adaptation using community sensor networks. Today is the first of our talks. We'll have 18 or 19 this year, or this week and the first week in November. Clinton, could you take it away?
Thanks, Charlie. And good morning and good afternoon and good evening, everybody. My name is Clint Andrews. As Charlie noticed, I'm a professor at Rutgers University. I'm cross-trained in the sense that I'm an engineer who turned bad and got interested in public policy questions. And that led me to a position running our Center for Urban Policy Research, where we these days have been focusing quite a bit on the twin challenges of climate change adaptation and mitigation. Today's talk is about adaptation and a special version of that where we are engaging with uh, community actors to try to empower them to take charge of their own lives as the climate changes. And so what I want to talk about today is a project that uh, introduces some work we're doing here in New Jersey in the city of Elizabeth. And I'll give you some background, do a quick tour of the instrumentation and of the types of analysis that we have been performing. And I want to spend a lot of time on the community activities that accompany this, because that's an important part of the whole story before wrapping up. And just to presage where I'm going, this cartoon illustrates urban life, especially uh, young people and elderly people who are more vulnerable to issues like heat stress and air pollution. And to highlight that we are monitoring outdoor conditions, indoor conditions, and personal exposures via mobile monitors. And this is not something that one does alone. I have Rutgers colleagues in several departments representing the schools of engineering, communication, environmental sciences, and planning and policy. And we have community partners, specifically Groundwork Elizabeth, which is a nonprofit group, and the Housing Authority of the City of Elizabeth, which provides social housing or affordable housing to uh, low-income residents. And this work has been supported with grants from the National Science Foundation and the U.S. Environmental Protection Agency, as well as some community foundations. And to help you locate all of this action, we are in the United States on its east coast, New Jersey, the most densely populated of the US states, with a population a little above 9 million people. And Elizabeth is one of the older cities. It's right on the water. It's special feature, which is important from an air pollution point of view, is that it has Newark International Airport on one side. It has the Bayway Petroleum Refinery on another side. It has the International Shipping Port of Newark and New York on the third side. And it has the New Jersey Turnpike running right through the middle of it. So this is a location that suffers quite a number of environmental insults. Another important thing to note at this point is that it's not a large city. Its diameter is roughly 5 kilometers. And so that's going to become important when we think about how we try to measure environmental conditions. Okay, and so uh, a lot of this work is motivated by public health concerns. Specifically, if you look at weather-related deaths in New Jersey, heat-related deaths are by far the most important, the largest number. And as I mentioned, this is a location with significant amount of air pollution, and that shows up in the high percentage of asthma hospitalizations that result in Elizabeth compared to elsewhere in the county and the state. We will focus especially on one air pollutant, particulate matter, PM 2.5, which is fine particulate matter with particles uh, under 2.5 microns in diameter. And compared to a human hair, that's just a fraction of the diameter of a human hair. And so in thinking about various environmental stressors, and especially in the world of climate change science, there's an awful lot of work that's done at the regional level with remote sensing from satellites. And from that, you can learn quite a bit. You can learn, for example, about the presence of an urban heat island. In other words, an area where uh, ground surface temperatures are higher than in surrounding areas because of what comes with a city. Lots of buildings that uh, give off heat, a lot of paved surfaces, which reduces the level of uh, permeable surface, and many of these surfaces are dark, as well as fewer trees that would provide shade and evapotranspiration. However, relying solely on remote sensing means you're going to miss a lot of important phenomena. And so we see landscape level sensor networks. And in the United States, the US EPA provides a good sensor, roughly one per county. That is helpful for detecting regional air movements, or such as when there are wildfires in Canada that send a plume of smoke southward. We're able to detect that using these sparse but high quality sensor networks at the landscape level. There's also uh, quite a bit of information available in some places from indoor sensors, because uh, you can put sensors right indoors and don't have to worry about the weather corroding the devices and so forth. And since we spend a lot of time indoors, that's really useful information. And then finally, you can think about personal sensors that are basically going to track your personal exposures to heat or to air pollution over the course of a 24-hour day. So you can understand where are you most severely exposed. And so this leads to our theory of the problem of uh, helping a population adapt to the health threats associated with climate change. And so we first want to understand, well, what are the outdoor drivers of exposure to heat and to air pollution? And so it's going to be factors like air pollutant emissions, temperature and humidity levels from just from what the weather is, uh, the extent of which there's sunlight today. And that yields conditions, measured in air pollutant concentrations and temperatures and humidity levels. There's a second set of drivers of environmental health stressors that are much more local, and that has to do with the presence of shade and trees, and the fact that there's hot spots and uh, problems associated, for example, with traffic congestion, where you get local air pollutants that are much more intense in their concentrations. There's a third set of drivers from a health perspective that are indoors, and that's our own behavior as we live indoors, um, cooking, smoking, cleaning, each of which uh, uh, gives off emissions in addition to changing temperature levels. And we try to mitigate these by opening or closing windows, by installing mechanical systems that provide heating, ventilating, and air conditioning. And so if we want to think about the human health impacts of environmental stressors, we really need to consider the outdoor factors, the local drivers, and the indoor drivers. And so that's our theory of the problem, is we want to measure each of those to some degree. So let's look at the instruments. On the far left is a traditional measurement station of the type that's used by the Environmental Protection Agency, one per county. These are very expensive, high quality instruments with big chain link fences around them to keep them intact. We have purchased uh, outdoor air monitors, indoor air monitors, mobile sensor packages, and personal sensors. And I'll talk about each of those and how we use them in the next couple of slides. First, want to give you a flavor for the built environment that we're working in. And so here are several of the Public Housing Authority sites in Elizabeth, New Jersey. And the key things to notice, these are all sites where elderly people live. Uh, so on the left is Mravlag Manor, which was built in 1938. It's 3 stories tall, 400 odd apartment units, and no central air conditioning. Uh, Next in the middle is John F. Kennedy Arms, and that's a senior building with 125 apartments in it, built in 1968. It's about 7, 8 stories tall. And it too has no central air conditioning. And instead, you see window air conditioners in some apartments. And then on the right is a newer facility built in 2011 to lead green building standards. It has 31 apartments in it with central air conditioning. And so part of what we uh, are able to do with this variety of housing types is to understand what's the role of the physical plant in determining people's exposures to heat and to air pollution. Okay, a quick tour of the devices. So as I mentioned, the traditional EPA monitoring station has wonderful equipment, costs a lot to install and a lot to operate. There's only 29 of them in the whole state of New Jersey for 9 million people. The instruments that we've installed are uh, set up to be weatherproof. They use a simpler technology, and instead of being $100,000 instruments, they are closer to being $5,000 to $10,000 instruments. And they measure a variety of what are known as the criteria air pollutants. So particulate matter of different sizes, carbon monoxide, nitrogen oxides of various types, ground level ozone, and temperature and humidity. And we also have indoors a set of much cheaper devices that cost maybe $200 to $300 each that are pretty good at measuring particulate matter, temperature, and humidity. We have other devices that we've been trying out. Uh, we are finding that in this mid-level range of say $5,000 to $10,000, not all of them are particularly reliable and trustworthy. Sometimes it's with the sensor, sometimes it's with the communications package associated with the sensor. Okay, so we ended up installing sensors at public housing sites throughout the city of Elizabeth. And this uh, shows the locations. And the main thing to gather is that they are in various places in the city. The EPA's monitoring station for the county lies at the bottom of this picture. And so that's a wonderful opportunity for us to co-locate some instruments there in order to see how well our instruments do compared to a gold standard instrument. And so here's the EPA monitoring site. It happens to be right next to a highway interchange for the New Jersey Turnpike. And there are some of our instruments installed uh, with the permission from the government minders. Okay, meanwhile, we have gone ahead and installed our sensors outside of many of the buildings throughout the city. And they're fairly innocuous. We put them up high enough so that vandals can't get to them, but still low enough to capture the experience of what people are going to be finding on the ground. Now, the communication linkages go from these deploying the sensors, each of which has a manufacturer, and and most of these manufacturers will uh, support the communication function as well. And they provide real-time data streaming to a central server. And then we download data from the central server which is out in the cloud someplace, to our own servers. And we perform computational modeling, and we uh, provide several outputs. We store raw data, we deliver modeled data, including projected data, predictions. And we also use this both to model and to track behavioral interventions, which I'll talk about more in a second. And then we push the outputs to a variety of platforms. And so this is hard to read, but each sensor um, is a row in a big database, and we can ensure that the sensors are operating with a quick check of the dashboard. Here's an illustration of some data that are thrown off, and this is PM 2.5 data for really just for a day or so. And we can see, for example, a change in the weather. A storm passed through town and dropped the PM 2.5 levels very dramatically as the rain washed the particles out of the air. Similarly, for ozone data, this is multi-day data, and you can see the diurnal pattern that's associated with ozone because you need both um, uh, nitrogen oxides and VOCs and sunlight in order to generate ground level ozone. And so it follows a predictable pattern. And in this case, in the latter couple of days, we are getting some exceedances. So we're getting high enough levels of ozone that it's considered a health concern. We've also been able to compare our sensors to the regulatory grade sensors to confirm that similar patterns in the data are emerging, and that helps us build confidence in our own numbers. Okay, indoors, these are consumer grade devices that communicate via Wi-Fi, and we're able to place them in a few dozen apartments across 3 different building types. And the biggest challenge has actually been maintaining the Wi-Fi connection. And so in some cases, we've had to install uh, sort of cell phone hotspots because the Wi-Fi provided by the housing authority wasn't serving that apartment particularly well. And finally, a category of instrument that has turned out to be full of insights are the mobile sensors, the portable sensors that, and we had 2 versions. We had a backpack version that has about $20,000 worth of different high quality sensors in it, which was not as helpful because it turns out the high quality sensors hate being moved and jostled around. And so they produced pretty lousy data. Uh, what turned out to be wonderful were these cute little sensors that are just about the size of a cigarette pack, and it can you can strap it to your belt, or you can hang it off of your purse, and it measures PM 2.5 and temperature and humidity levels right where you are. And it uh, can pair with the GPS in your cell phone so that you can get a geographic spatial trace of all this. And I'll talk about how we used them in a second. Okay, so a quick tour of the analytics. Um, there was a lot of mapping and modeling and analysis. And frankly, it's still going on because we built in a sense, an infrastructure that's allowing us to explore a whole variety of questions. And so uh, one, this sort of biggest uh, analytical frame is our digital twin, where we seek to represent the physical space, meaning the built and natural environments, the human activities in the community, and the sensors that are both in the scene and on person, to represent that digitally using multi-sourced urban data sets, as well as a variety of models, as well as analytics to consider human exposures and vulnerabilities. And so, in terms of the representing the physical environment, uh, that's a lot of it is GIS, sort of digital representations of space and the characteristics of the city. In terms of the sensors in the scene and the sensors on the person, as I mentioned, we had the backpacks, which turned out to be a little problematic, but we also had the more local sensors, both the fixed sensors indoors and outdoors, and the mobile sensors attached to people's belt loops. And then we shot LiDAR of most of the city so that we had a really good physical understanding of uh, where the city is, how things relate to one another, what's inside buildings, what's outside buildings, and where the sensors are. And we were able to do some successful prediction work, uh, taking both meteorological data and our sensor outputs and processing it to training a model and then doing predictions and um, uh, developing a stream of predictions of especially air quality to try to anticipate what conditions are going to be in a few hours. Uh, the understanding, this isn't only kind of a machine learning game, there's also a lot of physics-based modeling, which is important here, where we pay attention to the prevailing wind and the turbulence as that wind hits the sides of buildings, which is important for understanding the micro level variations in both heat and air pollution. And then we had to share all this with the residents of the city. And so I'll talk more about the importance of thinking through good visualizations. Okay, let me introduce some of the activities. This is not all of them by any stretch, but we were motivated in part by community-based participatory research objectives of not wanting to uh, be exploiting a community to get their data. Instead, we wanted to work with the community to provide things that were useful to them. Uh, uh, we did a lot of engagement work from air quality walks, carrying the backpacks and the belt loop sensors. We got the mayor to come on one so that there was the mayor's air quality walk. We did a whole variety of translational research activities for K through 12, so elementary and high school kids. And we did workshops on how to uh, do personal exposure measurements and air quality mapping. And I'll show you in a little bit more detail a couple of these. So there was a lot of talking here, engaging with community members, meeting with both, I'll call them the elite community members, the mayor, the head of the hospital system, the head of the tenants association, as well as with residents of public housing about what they experience and what their concerns are. One really fun thing that we did was a set of photo voice activities where we uh, gave people cameras or let them use their cell phone for a camera and asked them to go take pictures of uh, things in their community that spoke to them. And so a little quick sense of what you can learn from this is we asked them to take pictures of good air quality, of bad air quality, of heat stress. And these are things that in a sense are invisible, but they thought about, well, how do I experience heat stress? And so they took pictures of streets that were empty, of dying plants. In terms of air quality, they took pictures of uh, smoking and fire and industrial activities and lots of vehicles and hazy sky. And in a sort of an interesting way, things that to them evoked bad smells. And for good air, they took pictures of clear sky and of urban green spaces and of waterfront parks and things like that. And so they started to go from the objective to the subjective here to understand um, how they perceived these important environmental stressors to which they're having to adapt. All of this was really helpful in designing interfaces to communicate to community members. And we really wanted to make sure that we had dashboards that were easily accessible and interpretable and easy to navigate and full of informative content and scalable and working across devices and so forth. And so we went, that's, anyone who's worked in this area in the UX space knows you have to do iterative prototyping and development and checking back to see whether things got better or not and identifying key interface elements that you need to arrange in some fashion. And that finally led to this dashboard, uh, and it's entitled the Breathe Dashboard, which is a very awkward acronym for Better Regional Elizabeth Air Tracking and Health Evaluation. Uh, we made sure that the dashboard worked on a cell phone interface as well as a computer interface. And then we made a separate dashboard for the public displays that are in all of the housing authority buildings, these community knowledge boards. And again, we went through the iterative prototyping process to come up with a pattern that here's what it looks like on a day when it's in early July when the air quality is good and the heat isn't too bad yet. And so it suggests, consider going outdoors. Um, you probably don't need a mask or air purifier today. And so why not take a walk? And then it changes when the temperature gets too high and it says heat warning. And here the suggestion is stay hydrated. Don't go outside. This is what the dashboard looks like as of a couple of days ago when I put these slides together. And so you can see it's adaptive. It translates the numbers into suggested activities and interpretations, and it provides a QR code for more details for anybody who wants it. And here's a snapshot from a couple of days ago of our more detailed dashboard that provides the time history for each sensor and lets you quickly gauge whether things are good or bad, and everything's green today, so that's good to see. And if you want more detail, you can click on any one of the sensor icons and download its historical measurements. And it too is adaptive, changing color and changing the set of recommendations that are offered depending on air pollution levels and temperature and humidity levels. Okay, I want to take a little bit deeper dive into personal exposure measurement because this turned out to throw off some really useful insights. And it may seem shocking to want to study climate change adaptation at the level of the individual person, but that turns out to be useful. Um, First, it measures actual exposures that people experience. It identifies moments when they might be in a trade-off situation. Do I go out in the heat or do I stay in my polluted apartment? And it turns out to provide a really clear way to communicate about risk. It puts these risk considerations into the familiar context of everyday life. And that means, for example, thinking about, well, should I stay indoors or go outdoors? And that's going to depend on relative conditions. And of course, also, what are the attractions out there? And there's both the acute, extreme heat days or terrible air pollution days, or if there's a fire indoors, but also the more daily activities. What's the weather out? Is there is today the day to go to church or to go shopping? In operational terms, it helps people figure out some basics like should I open or close the windows? And that's going to depend on relative conditions indoors and outdoors, including not only the thermal and air quality issues, but also factors like noise. And then finally, it's going to help people think about spending money. Which kind of heating, ventilating, and air conditioning equipment should I buy? Uh, do I need those extra filters to improve air quality? So we did our personal exposure measurements in partnership with community members and got them to fill out diaries. They would wear the sensor for 3 days and keep a diary for each of those 3 days about where did they spend their time, were they indoors, were they outdoors, what were they doing. And then when we gave them back their sensor traces, this represents several days worth of heat index measurements for a person. They annotated what they were doing in each part of the day, and they learned that uh, their highest heat index exposures were actually in one day it was when they were at home and had no air conditioning, and in another day when they were out walking. And so they were able to really link their behavior and their circumstance to their exposures. And uh, showing traces of both the heat index, which is basically a polynomial relationship between temperature and relative humidity, and labeling it to see, aha, okay, it was during my lunch and errands that I had the highest heat index exposure. And then also the PM 2.5, the particulate matter exposures, um, which had a few very high excursions and then a lot of fairly low level exposures. One thing we discovered was that we needed to borrow a tool from the electric power industry. And in some cases, where you could show what's on the left, which is an hourly heat index profile, um, and identify key metrics from it, like an exceedance duration, when the heat index is above some threshold level, as well as things like what is the daily range, what's the mean, median, minimum, and maximum heat index experienced during a day. We found it useful to create a duration curve version of this and to have a daily heat index exposure duration curve. And that provided a much clearer um, understanding of how the minimum heat index related to the median, related to the mean, related to the threshold level, health-related threshold level, that related to the maximum heat index. It also provided a more intuitive way to show what the range of daily exposures was and what the exceedance duration level was. And so in this example, uh, the person was exposed to, for a little less than 15% of their day was exposed to extreme heat. And so if you look at uh, exposure duration curves for heat index, this is looking at one person uh, uh, for three different levels of sensor. So the outdoor sensors that we had on the sides of the buildings, which are in the black line, the indoor sensors, which are in their apartments, which is the blue line, and then their personal exposures. Now, as you'd expect, most of the time the personal exposures lie between the measured indoor and outdoor exposures, where because people spend most of their time indoors, that dominates. Um, but there's one interesting artifact shown here, which is the indoor measurements only capture uh, what's going on in the person's apartment. And that day, they also spent some time indoors at a shopping mall, which has much lower temperatures. You can do this type of analysis person by person by person, or you can look at groups and see how young people, high school age kids in our case, um, how they compare to working age people who housing authority staff, and how they compare to the seniors who are living in the public housing. And what we noticed across these three populations was that the seniors stood out for having much better, I'd call it, heat exposure management behaviors than the youth or the working age folks. The working age people were stuck. They had to go outside and mow the lawn, even if it was hot. The youth, it's much more their own uh, behaviors, and they just didn't care as much about heat exposure. And so they found themselves having a fairly high percentage of hours above a heat index threshold, unlike the seniors who had almost no hours above that threshold. Um, and uh, Again, looking at the 24-hour day version of the story, and then contrasting the exposure duration curve version of the story, it becomes clearer for this one person uh, how they had done pretty well at managing the percent of the day that they're exposed to extreme heat. But there was a real spike in air pollution exposures that represented fully 5% of their 24-hour day. And that's enough to cause some concerns about health. Um, okay, I want to keep going into an example of some modeling work that we did. And this is using a wonderful tool that NIST produces called CONTAM that allows you to simulate indoor air quality based on real buildings that you then create a model of. And you take outdoor and indoor sensor measurements to help calibrate the model. And then you test out different behaviors. And so, in the spirit of running scenarios, we looked at three different levels of ambient outdoor conditions. We looked at window opening behavior and using uh, air filters and found, I'm just going to illustrate one of those scenarios, which shows how indoor air quality is partly influenced by what's going on outdoors. This is for a very bad air quality day, but partly by people's behaviors. The two spikes represent cooking a meal on a gas stove, and the lower part in the middle represents using an air purifier, and then the bump in the very middle represents a period when windows were opening. And so we can model this and then share the results with uh, the residents. Uh, a final activity to illustrate how this translates into action is the residents decided they saw that there was this trade-off that they were experiencing between wanting to stay indoors out of the heat, but finding that the air quality was poor because of cooking, because of burning incense and candles, because some people smoked. Um, and so they wanted to find out if there's a cheap way to clean the air. And so we did some research and came up with this idea of getting an inexpensive box fan and duct taping a furnace air filter to the fan. And then we tested that in the lab and confirmed that it worked just as well as the $300 air purifiers you can buy from Amazon. And we had the high school students build these and give them to the seniors who then have been using them in their apartments. So to wrap this up and see if there's some questions, what I think I've been able to illustrate here is that a community university partnership is valuable. It has this uh, attribute of balancing the science push, what we professors and grad school students think is important, and demand pull, what the residents think is important, and to ensure that we somehow meet in the middle and do things that are useful to residents and understandable by residents, but still have scientific rigor. We identified that there are many, many adaptive actions that are available to residents, as well as to local and national governments, as well as to businesses and nonprofits. And so we felt like we expanded the solution space for adapting to climate change. It's clear that residents adapt at an individual level by resolving trade-offs between thermal comfort considerations and air quality considerations. And they do have to do this in the context of lots of other factors, like I need to go to work, I need to go shopping. Uh, and then finally, we found that especially by framing things personally, we were able to communicate the risks and identify the solutions quite well as a part of this partnership with the community. So uh, I'll stop there. I'll leave this up for a second. If anybody wants to go look at our community bulletin board or our project dashboard, here are the URLs. But why don't I stop and see if there's some questions or comments?
Okay, Clinton, why don't you leave this slide up? Um, and while we're talking, if you can, you might want to paste some of those links into the chat.
Good
Um,
idea.
um, Ravinder had a question. One challenge with these sensors is their higher costs, making wider adoption challenging, particularly for low-income countries where climate changes are relatively higher, and as many um, these countries are on steep growth curves. What do you think about that aspect?
Yeah, I think that's very important. Although there's an interesting twist on that, which is that a lot of these, especially the personal sensors and the consumer grade indoor sensors, uh, really got their boost uh, by people in places like Delhi or Beijing who were frustrated by the terrible air quality they were experiencing outdoors and were finding that they couldn't get good information from their own governments. And so they took it into their hands to start um, buying these consumer grade sensors. And then that data gets put up on the cloud for the world to see. And in that process, embarrassed some governments into trying to make improvements. Um, there is this, one of the things that I feel we've learned, however, is that the regulatory grade sensors that, where you're dropping probably a $500,000 US dollars or more, maybe $1 million US dollars in one sensor site, a regulatory grade site. Um, it turns out that the $5,000 sensors work really well. They track quite closely. Um, they do have the challenges of eventually um, getting out of calibration so that there's a what I would call a short-term versus long-term issue there to manage.
Okay, that's a good point. If you want to continue pasting, that'd be good, or return to your slide. Um, I had a silly question for you. Your list of threats and concerns was clearly New Jersey oriented. You didn't have tornadoes on there. You didn't have fires. You didn't have earthquakes. Earthquakes are always a concern in California. So,
It's true, but I would take the point that if you're going to communicate with real people who live somewhere, then you need to find out what are the threats that are relevant to them.
good point. You got me there. Um, I see some other questions, but I have some. It didn't look like you had many single family dwellings because of the nature of your study. Would you want to include more of those?
Yeah, that's a great point. I'm struggling to get the chat to work for some reason. Um, uh,
I'll read from them, so it's
okay.
okay.
Uh, uh, we have parallel studies in the leafy suburbs of New Jersey, and um, I have one of those devices in my own home, and uh, the things that we find that drive uh, the air pollution levels are identical to what you see in multifamily housing. It's cooking, it's outdoor conditions, it's burning candles or incense. And so the drivers are quite similar because the activities of daily life are quite similar. Uh, the the bigger differences that we've been seeing seem to have to do with uh, factors like your occupational exposures. Do you have to work outside or not? And that's of course, that's widely known, and that's why we have in most countries some version of an occupational um, safety and health administration that tries to set guidelines of uh, what's what's allowable. Uh, that's been a big um, debate in this country because different states have more or less friendliness towards labor law, towards labor policies. So, for example, Texas has, uh, even though it's terribly hot in Texas, they don't want to regulate what what employers have to do to protect uh, construction workers and farm workers. Whereas in New Jersey, there seems to be more willingness to provide guidance to employers about what's acceptable.
And then another question for you is, as a microwave engineer, I always hear concerns about EM exposure, low frequency 60 hertz on one hand, and on the other hand, ultra high frequency to millimeter wave. I wonder if an EM sensor module has any commercial value. Do you think one might?
Um, there are some that exist. I don't know who buys them. I suspect they are mostly in Northern California and are um, worried about uh, uh, so I in IEEE world, I'm usually associated with either the Power and Energy Society or with the Society on Social Implications of Technology. And um, my good buddy Ken Foster, who was part of SSIT and a professor down at Penn, University of Pennsylvania, he had a book called Phantom Risk that tried to characterize the challenge of proving a negative.
Okay. Here's a question, which I'll reword. A mall might be consuming a lot of energy and ejecting pollutants into the environment. So how does it end up that a mall reduces personal exposure?
Because when you're in that mall, you're enjoying the air conditioning. And it's true, it takes energy to air condition. Um, but that may be a trade-off society's willing to make. Um, there are some people in the environmental health space who are, I would call it fairly ideological in saying we think that humans should adapt to conditions that exist, and rather than change the conditions, we should increase our adaptability, our sort of physiological adaptability. That may make sense for young, healthy people. It makes less sense if you're elderly and asthmatic and have some cardiopulmonary uh, challenges. That's just a recipe for having an acute, having heat stroke and ending up in the hospital. And so I am an unabashed advocate um, of allowing cooling in as many places as want cooling.
Yeah.
This is actually an interesting area where Texas is ahead of New Jersey because at least the city of Houston has in landlord-tenant agreements, uh, in addition to as part of the guarantee of habitability, when if you rent, it should be a habitable place to live. That means providing some minimum level of space heating during the winter, but it also in Houston means providing some minimum level of cooling during the summer. That is, the right to cooling is something that has not yet permeated the northeastern part of this country. Uh,
Huh.
that's an area where I think the international experience across IEEE members, we could have a good conversation about that.
That's a good point. Another question was in the context of scaling up climate change mitigation through clean energy policy, what are the most critical bottlenecks for the wider implementation of solar energy generation? And are of those challenges, which ones require the most urgent action from local decision makers?
Okay, yeah, interesting. It's not what I talked about today. Today was about adaptation, but on the mitigation side of things, especially for solar, uh, the key things have been uh, uh, driving down the unit cost per watt of solar, and that has happened in large part early advances in the United States and other countries, and then really major advances in China in the last decade that have dropped the cost of solar panels by an order of magnitude. And at this point, they are cost competitive without subsidy for utility scale applications, multi-megawatt applications. They still need subsidies, at least in this country, for rooftop applications on individual homes. Um, there was an so the bottlenecks are uh, actually a list of current policy initiatives out of our White House represent a good set of bottlenecks. Tariffs that impede trade between countries when one country has a comparative advantage in producing cheap solar panels. Um, uh, Realigning subsidy regimes to favor fossil fuels and to disadvantage renewables.
Yeah,
And then um, the third category, which has been very important in many locations, are the soft costs. In other words, uh, tailoring solar panel installations because it's basically an electrical system and you need a licensed electrician to install them, tailoring them to local requirements. And this has been an area where generational change in electrical inspectors seems to be part of what's needed to get them to know how to review the work of the solar installers and to ensure quality control on that and to have it be treated as just any other electrical system.
Okay. What about chlorine, hydrogen sulfide, natural gas, radiation, or other sensors? Which ones would you like to add to your suite?
Um, I would be quite interested in adding fugitive methane emission measurement, partly in both indoors and outdoors. Indoors because we have a lot of old gas stoves, especially in rental housing, that are really in bad shape and are adding pollutants to indoor air. But outdoors because it's a very potent greenhouse gas, and a lot of uh, emissions are unintended emissions from sewage treatment plants and from leaking gas pipeline compressors and other sources like that.
Which got more use for your viewing things, the cell phone or the computer interface?
The cell phone interface by far.
Okay. I found your public displays to be interesting too. I think in a large housing area with a common area, that'd be interesting.
Yeah,
Um,
it's basically tapping into communication media that already exist and making the most of them. That 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 was the strategy that turned out to work.
uh, so again, if you have a question, put it in the chat. I have another one for you. In the 1960s, when plans for satellite-based sensors were conceived, the idea that millions of sensors could be deployed was inconceivable. But with the IoT and commercial electronics, it's possible today. What is best by satellite and best by sensor networks?
So satellite is great for characterizing regional air pollutants or regional environmental stressors. The the urban heat island is an example, or tropospheric ground level ozone is a regional pollutant. But if you're going to try to measure things like particulate matter, uh, that needs to be much more fine-grained because the exposure can vary just by moving a few meters back from the edge of the busy highway. And so I see them as complementary rather than as substitutes.
Okay. Do you have any final comments? It looks like we're out of questions. Do you have any closing comments you'd like to make?
Um, just that I think this is an example of how engineers and scientists can work really constructively with community members, and that the benefits are both scientific and um, practical because people understand what you're saying much better when they have had a chance to be involved in it. And, in the case of the personal exposure measurement, where they've seen how their own personal daily activities link to these bigger picture concerns.